Understanding. Hi, I'm good morning, one and all. Hi, I'm Vishal. I'm from Electrical and Electronics Engineering Department. I'm here to explain about understanding a type of forced oscillation caused by steam turbine governors. So here we are going to learn about the oscillation caused by steam turbine governors. Let, let's go into let's go into this. Yes. Governors are essential components of primary frequency regulation in a power system. However, many oscillation events indicate that a governor system, if not configured properly, can induce sustained oscillation of a power transmission system. A malfunctioning extractor valve of a steam turbine is considered to be the oscillation source of the Western American oscillation event. A hydropower plant operating in its rough zone caused the 0.37 Hz forced oscillation of the Western interconnection. Changes in the control mode of a governor system in Shandong power grid of China caused sustained peak grid oscillations in June. Another sustained oscillation event in China, Southern Power Grid, which was also mainly caused by a steam turbine governor. This paper studies the mechanism of a type of forced system oscillation caused by a steam turbine governor, which is found to be driven by a limit cycle due to imperfect compensation of the nonlinear valve characteristics within the turbine. Then an imperfection index is proposed to evaluate the residual nonlinearity and discover how a limit cycle can occur and cause forced oscillation. So here the mechanism of governor induced oscillation. So to To understand the mechanism of this type of oscillation, consider the small signal model of a single machine infinite bus system. Two h by omega. Here the equation is 2h by omega naught into delta s delta into rho plus k k d by omega naught into delta into rho plus ks into delta rho plus is equals to delta into tm. Here delta into rho is equals to delta into omega. So we have read the equation here. So here where Ks and Kd are synchronous torque and damping torque. Here Ks and Kd are synchronous torque and damping torque coefficients. 2h is the inertia constant and omega naught is the synchronous angular speed controlled by its governor. The mechanical power can be expressed by delta Tm minus delta omega G GOV of SF into delta omega plus AM cos omega MT is the equation here. GOV of S, it is a transfer function of a linear component of the governor. F of delta omega represents the governor's non-linear component depending on the size of speed deviation. And delta omega here the so we can see that ks and kd are synchronous torque and damping torque. 2h is the inertia constant, omega naught is the synchronous angular speed. Synchronous angular speed, delta Tm minus delta omega G into GOV of S of F into delta omega plus Am cos omega Mt. For example, if For example, if governor deadband is considered f of delta omega is equals to 0, then delta omega is within a threshold am cos omega mt represents an external periodic disturbance which may be introduced by other unmodeled effects with the steam turbine power plant. A non-linear equations can express the system as follows. Here we can see the matrices. Here the delta into rho matrix column delta into rho dot next line delta into omega. So is equals to in matrices 0 1 minus omega naught ks by 2h minus kd by 2h into 1 plus omega naught by kd g into gov of s into f into delta omega into delta s in the matrices delta into matrix delta s delta omega. How to express the non-linearity? It is very important to understand the mechanism of oscillation caused by governor systems. Here we use a polynomial to show the non-linearity of governor systems. Since it is convenient to obtain parameters of a polynomial from the original data, f of delta omega is equals to summation I is equals to 0 up to n ai of delta omega of I, where n and ai are the order and coefficient of the polynomial. Illustrates the power oscillations in time domain and the phase space for three typical cases. Here in a case 1, am is equals to 0, no external periodic disturbance, and f of delta omega. Ignoring non-linearity, the mechanical power is decomposed as delta Tm is equals to minus Ks m delta S minus of Kdm by omega naught into delta omega. Here, Ksm and Kdm are the mechanical synchronous torque and damping torque coefficients, and they can be derived from the decomposition of G into G of G of S. Let 2h is equals to 1, k is equals to omega naught of k into ks plus ksm is equals to 3, and b is equals to kd plus kdm. Take three different values 0.1 and 0.2. Here in case A, in case B, here am greater than 0 with an external periodic disturbance and system has sufficient damping. Let 2h is equals to 1, k is equals to omega naught of ks plus ksm is equals to 2, b is equals to kd plus kdm is equals to 3, am is equals to 8 by omega naught, 10 by omega naught and 12 by omega naught. In case C, am is equals to 0 and consider the non-linearity of f of delta omega. Let 2h is equals to 1, w omega naught ks is equals to 1, kd is equals to minus 1.5, and the order polynomial n is equals to 2, 3 and 5 here. So these three cases illustrate different cases of three types of sustained oscillations. The first type is caused by insufficient or negative damping of natural mode of a small signal model. In the other two types are usually considered forced oscillation, since the source of oscillations are not inherent with the small signal model of the system. The second type is caused by an external periodic disturbance, and the third is driven by a limit cycle arising from a nonlinear component of the governing system as modeled by the polynomial function f of delta omega. Here we can see the graphs in A. Sustained natural oscillations. In B. Sustained oscillation driven by an external periodic source. In third case, sustained oscillation driven by non-linear limit cycles. Thank you so much.